Let's talk about the second method to show there is no Hamiltonian cycle. So here we have the same graph. The first thing we do is we want to count the number of edges. Let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So we have 21 edges. So in this process, we have to be patient and make sure we have the correct number of the edges. And then let's count the number of vertices. Okay, so let's erase all of our mark. Let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 vertices. Okay, so because each vertex has degree 2 in the Hamiltonian cycle. So each vertex has degree 2 in the Hamiltonian cycle. So let's label minus the number of eliminating edges. Okay, so now let's see. Look at A. A, now the degree is 2, but 2 is good, right? Because we want to have degree 2 in the Hamiltonian cycle. So the vertex A is okay. But how about B? You can see B, the degree is 4, but we only need 2, so which means we need to eliminate 2 edge connecting B. And C, the degree is 2, so that is okay. And then how about G? You see the G is degree 4, but we just need 2, so we want to eliminate 2 edges. And the D, we have degree 3, so that's why we want to eliminate 1 edge. And then the E, we have degree 4, so we want to eliminate 2 edges. F, we have degree 3, so we want to eliminate 1 edges. And then K has degree 4, we want to eliminate 2 edges. And then H has degree 4, we want to eliminate 2 edges. I is okay because it has degree 2. And J has degree 4, we want to eliminate 2 edges. And L has degree 3, we want to eliminate 1 edge. And then M has degree 3, we also want to eliminate 1 edge. So now we have checked all the vertices, okay? And we already label the minus the number of eliminating edges connecting to incident to that vertex. Okay, so now what are the number of eliminating edges? Okay, so what we do is we first look at the vertices with the biggest label, okay? I mean biggest in the magnitude. So let's look at B. Do you see B? We want to eliminate 2 edges, okay? And then we can see A and C, we don't eliminate edges. So it's either connecting the D or F, okay? So here we know if we eliminate 1 edge, that edge is counting in the label of B and D, okay? So that's why here the D, we don't highlight it, okay? Because when we eliminate 2 edges from the vertex B, then 1 edge of D must already be eliminated. So we don't mark the D, but we mark the E. Okay, so we don't mark the adjacent vertex to B. We mark the next two vertices, okay? So we mark the E, and E is adjacent to F, so don't mark the F, but then we can mark the K, okay? So we mark the K, and then you can see M is adjacent to K, so don't mark the M, because when we eliminate the two edges from the vertex K, the M, because it's adjacent to K, maybe we eliminate the edge MK, then the edges counted in the K and in the M, so we don't want to mark the M. And then we want to mark the L, okay? And L is adjacent to J, so don't mark the J. And L is adjacent to H, don't mark the H. And then we can mark the G, okay? So look at the yellow highlighted vertex. We count the number on that vertex. So B, we have 2. E, we have 2. K, we have 2. G, we have 2. L, we have 1. Add them all up, we get 9. Okay, so here we only count the yellow parts. Okay. So how do we get the yellow part? First, we pick a vertex with the biggest magnitude label. Okay, let's say B, and then we highlight it with yellow. And then we don't count the adjacent vertex. So we don't count D and F. Then we will see we can count E, right? And then we can also count K, but don't count J. And then we see M is adjacent to K, so don't count the M, but count the L. Okay, so so for example, let's see. Let me draw it here. Okay. So we count this one. So count this one, but don't count this one, because you don't want to double count the edges, right? Okay, so now what is the number of edges left? We have, so left in the Hamiltonian cycle, we have 21 minus 9, which is 12. Do you see this 12 is different than the number of vertices? But in a Hamiltonian cycle, the number of vertices equals to the number of edges. Okay, so that's why if we see those numbers are different, we get a contradiction. So different, here we get a contradiction. So there is no Hamiltonian cycle. So this is method 2. Okay, so you can see the same problem we can solve using method 1. We can also solve using method 2. And when to use method 1, if we have like a vertices with degree 2, we can use method 1, because we can first look at the vertices with degree 2 and try to think about what edges we should keep and what edges to eliminate, and try to derive some contradiction. And if we have a graph that we don't have many vertices with degree 2, maybe we have none, we have no vertices with degree 2, the method 2 is useful. So here are some examples of your homework. So you can pause the video and try to work on those problems, and you can continue to play the videos. So let's see. Okay, look at this is number 4 in your homework. You can see there is no vertices with degree 2. So in this case, method 2 is easier. Because think about it, if we don't have vertices with degree 2, well then if you look at the vertex A, then we know we want to eliminate one of the edge. But there are 3 choices, right? We don't know which one to eliminate. So if we want to use method 1, we need to separate into cases. And each subcases, well, you look at F, okay, and then you have the other cases which edge we want to eliminate. So, well, it gives us a lot of possibilities to consider. So method 1 is hard. So let's use method 2. So again, we want to count the number of edges, right? So number of edges that equals, okay, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So we have 27. Well, yes, if we have a picture with a lot of edges, we need to slow down and you can put a little mark on the edges to count it, okay? So we have 27 edges. And then we count the number of vertices. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 vertices. Okay, and then now we know each vertex has degree 2. Let's put the label on each of the vertex. So let's look at F. F has degree 3. We know we need to subtract 1. A, degree 3, so subtract 1. B, degree 3, need to subtract 1. K, degree 3, subtract 1. P, degree 3, subtract 1. O, degree 3, subtract 1. G, degree 3, subtract 1. C, degree, what is that? 1, 2, 3, 4, 5. 5. So we need to subtract what? We need to have 2, right? So we subtract 3. D, degree 3, subtract 1. E, degree 3, subtract 1. H, degree 3, subtract 1. I, degree 3, subtract 1. L, degree 3, subtract 1. J, degree 5, subtract 3. M, degree 5, subtract 3. N, degree 3, subtract 1. So now we have put all the labels on the vertices. Let's count the number of eliminating edges. So let's highlight it with yellow. Okay, so we first find the vertices. We find the vertices with the biggest magnitude label. Okay, so we can see here C has labeled the -3, right? Okay, so we highlight the vertex C, but we don't highlight the adjacent vertex. So we don't highlight A, we don't highlight G, but then we can highlight F. We don't highlight D, but we can highlight B, right? We don't highlight E, but we can highlight J. We don't highlight E, but we can highlight I. We don't highlight H, but we can highlight M. Then look at J. J is next to the adjacent to N, so we don't highlight N, but we can highlight P. And then K is adjacent to J, so don't highlight K. O is adjacent to M, don't highlight O. So now you can see we first pick the maximum magnitude label to highlight it. And then we don't highlight the adjacent one, but we highlight the next one. The next two, okay? Alright, so now you can see all the vertices highlighted yellow. Let's count the label. So C, we have vertex 3. Sorry. Okay. Okay. So let's count. We have 3, that's C, and B is 1. F is 1. I is 1. J is 3. M is 3. P is 1. So you can see we have 3 copies of 3, that is 9. And 1, 2, 3, 4. 4 copies of 1. So 9 plus 4 is 13. Okay, so the number of eliminating edges is 13. Okay, so let's see. Then what is the number of edges left in the Hamiltonian cycle? That's 27, but we want to eliminate 13 of it. So the answer is 14. Oh, can you see 14 and 16? They are different. So we get a contradiction. So there is no Hamiltonian cycle. Okay, so this is method 2. Let's do one more example. Again, please try it first. It's on your homework. Okay, so pause it and try it. Are you ready? Then continue to play the video. Let's check our answer. You can see in this picture, we don't have vertices with degree 2. So that's why we need method 2. Okay, so number of edges. What is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 edges. And what is the number of vertices? Okay, let's erase our mark. 1, 2, 3, 4, 5, 6, 7. So we have 7 vertices. Okay, and then what is the number of eliminating edges? Okay, let's put the label. So C has degree 4, so -2. A has degree 3, -1. B has degree 3, -1. E has degree 5, -3. D has degree 3, -1. F has degree 3, -1. G has degree 3, -1. Okay, now after we put all the labels, let's highlight the vertices that we want to count. So which one is the biggest? Sorry. Okay. Which one is the biggest? We have E is the biggest. And then you can see B is adjacent to E, so don't count B. A is adjacent to E, don't count A. D is adjacent to E, don't count D, but we can count C. G is adjacent to E, don't count G, but we can count F. Okay, so here are all the vertices that we can count. Let's add them together. So we have 3. I thought I chose orange already, right? Yeah. So that is 3 plus 2 plus 1, which is 6. Okay, how about the number of edges left? In the Hamiltonian cycle, we have 12 edges total, minus the number 6 we want to eliminate. The answer is 6. Do you see they are different? So we get a contradiction. Remember, in the Hamiltonian cycle, the number of vertices equals to the number of edges, right? So that's why no Hamiltonian cycle. All right, so now we have shown 2 methods. Okay, so all right, let's make a summary. So there are 3 ways of determining if there is a Hamiltonian cycle or not. Okay, first exhaustively look for one until you give up or you can find one. So this is good for small graphs. And then we have our method 1, right? A graph with n vertices must have n edges in the Hamiltonian cycle. If any vertex has degree 2, the edges incident to that vertex must be included. If a vertex has degree more than 2, we must eliminate edges. So start with a vertex with degree 2, then go to the adjacent vertices to eliminate edges. Show that leads to a contradiction. So this is useful if in the graph we have some vertices with degree 2, then we can start with those vertices. But what if we don't have a vertex with degree 2? Then we need the second method. So we count the number of edges, and then we look at the degrees of all vertices to find the number of eliminating edges, and check whether the edges left, so m minus n is the number of edges left. Check if this number equals the number of vertices. If yes, then there could be a Hamiltonian cycle. If no, then there is no Hamiltonian cycle. Okay, so, and if yes, so like I said, there could be a Hamiltonian cycle, then you just find it. Okay, if no, then we know if we get a contradiction, then there's no Hamiltonian cycle. Again, there are no verified necessary and sufficient condition knowns for the existence of a Hamiltonian cycle in a graph. So these are the 3 methods, okay? So to show it has a Hamiltonian cycle, you just find it, okay? And to show there is no Hamiltonian cycle, we introduce 2 methods, okay? And remember, for Euler cycle, we can check the degrees of the vertices. If we have a vertex with odd degree, we know there is no Euler cycle, okay? And then if all the vertices have even degrees, we know there must be an Euler cycle. So you just find one Euler cycle in that case. So let's continue in the next video. See you soon.